Welcome to the Crazy Hat Chemist. So here we are, stoichiometry and dimensional analysis. We are almost up to the end here. We are on 10.1 today, limiting reagent problems and percent yield. So let's check this out for a limiting reagent problem first. Here we go. Bam! So the first thing I want to do is give you an analogy on a limiting reagent problem. And we're going to pretend that we're going to make a sandwich. And that looks like a delicious sandwich right there. Definitely. So we're going to make a really simple sandwich. So suppose you have a loaf of bread. That's going to say I have 24 slices of bread and a small package of turkey. That's 5 slices of turkey in that one package. And you want to make some sandwiches for your friends. So our definition of a sandwich is the following. It's 2 slices of bread and 1 slice of turkey. Okay? So, how many complete sandwiches can you make with 24 slices of bread, that's our bread loaf, and 5 slices of turkey? How many total sandwiches can you make? Given our definition of 2 slices of bread and 1 slice of turkey makes a sandwich. That is right, 5 sandwiches. And with 5 sandwiches, you will consume 10 slices of bread and 5 slices of turkey. So, what limits the number of sandwiches you can make? Well, it is the turkey. It is the 5 slices of turkey, and this turkey is now the limiting reagent. Okay? Hopefully that makes sense for you. It limits the total number of sandwiches you can make. Now, what is in excess? What is left over and not used, for example. And that is the bread, because you have more bread than you can use. So how much bread is in excess? That's in abundance. Okay? So we're going to take our 24 slices that we have available to us. We're going to subtract the amount that we used, which is our 10 slices, and we have 14 slices of bread in excess. So, the bread is in excess, the turkey is our limiting reagent, the turkey is completely consumed. Okay? So, I want you to think about this as we go through these problems. You can think about a pizza and the toppings on a pizza, whatever you want, and sometimes when you go to a fancy restaurant, you get leftovers in an aluminum foil container just like that. If you are making anything at a manufacturing plant of any kind, it doesn't matter what it is, but cell phones, computers, cars, they are composed of multiple parts. And as you put those parts together, you're hoping as a manufacturer that you have the correct ratio of parts. But if you have an excess number of parts, you need to get more of the non-excess, the ones that are limiting. All right, so hopefully that analogy worked for you. Let's carry on with the real problem. Bam! So, we're going to read this here real carefully here. 0.872 grams of aluminum metal reacts with 0.854 grams of oxygen to produce a single product. How many grams of product is produced? How much of the reactant is in excess remains? So, the first thing that we need to do is come up with a balanced equation just like every time we have a stoichiometry problem. So we have aluminum metal, that's a solid, and oxygen gas, okay? So, and it produces a single product, so that tells you what type of reaction is this? It's a combination type of reaction. So I'm going to take the charge on aluminum and the charge on the oxygen and look at those two numbers there. These are both periodic trends. I'm going to take the 3 plus charge on the aluminum, the 2 minus charge on the oxide, absolute value of those, flip the numbers, bring it down, and I get my formula, Al2O3. That's going to be a solid. Now you're going to balance this equation, okay? So I want you to pause the video really quickly here, come up with the product here correctly, the state of matter, and then balance it, and then, bam, here is our balanced equation. So hopefully that works out well for you, okay? Now, what we have here is the following. We have aluminum and we have oxygen. So how do you know it's a limiting reagent problem? You know it's a limiting reagent problem when you have numbers for both reactants. If you have a number for a reactant and a product, it's probably a percent yield problem. But if you have numbers for both reactants, then it's a limiting reagent problem. Okay? And here's the other key here. And then it makes it more difficult than our sandwich example. Okay? if I look at the 0.872 grams of aluminum and the 0.854 grams of oxygen, I cannot directly compare those numbers. I cannot directly compare those numbers because they do not have the same formula. You can only compare the numbers when you have the same units and formula. So that's my end goal that I'm going to try to reach here. Now, ultimately on this problem, I want to get how much product is produced in mass. So what I'm going to do is I'm going to carry both of these numbers to that product. So I'm going to take the aluminum and carry it to the aluminum oxide. I'm going to take the oxygen and take it to the aluminum oxide. So again, what I want you to do is to do the following. You're going to take 0.872 grams of aluminum metal and convert it to moles of aluminum. Then use the mole ratio from aluminum to aluminum oxide, okay, and then take the moles of aluminum oxide and convert it to grams of aluminum oxide. That's one chain of stoichiometry right there. That's one monorail. Now what I want you to do is to do another one. Take the 0.854 grams of the 0.854 grams of oxygen. Convert that to moles of oxygen using the molar mass of molecular oxygen. Then take the mole ratio between the oxygen and the aluminum oxide and convert that to moles of aluminum oxide. Then convert the moles of aluminum oxide into grams of aluminum oxide. So I want you to pause the video and I want you to do that right now. And then you're going to unpause and here we go. This is our first stoichiometry monorail. I've taken the grams of aluminum, converted it to moles of aluminum using the molar mass. Then I've used the mole ratio of aluminum and aluminum oxide and then the molar mass for aluminum oxide. And now I'm going to have grams of aluminum oxide. This is my mole ratio. Those are coming from the stoichiometric coefficients on that balanced equation in the yellow. I'm going to do the same thing with the other reactant. And I'm going to do the same process. I'm going to take the grams of oxygen, convert it to moles of oxygen using the molar mass, using the mole ratio. And then now I have moles of aluminum oxide, then convert it to grams of aluminum oxide. Now I have these two numbers right here in my calculator and I have highlighted with the arrow where you're going to round because both the beginning numbers have 3 significant figures and there are no fewer significant figures in the rest of the problem. So now I have two numbers right here. I have 1.65 grams of aluminum oxide and 1.81 grams of aluminum oxide. So now what we're going to do here, this is the easy part, hopefully. You've done the difficult part, and those the 2 monorails and the balancing of that equation. Now what we're going to do is we are going to compare the 1.65 and the 1.81. And the only reason why we can compare those two numbers is that they both have the same units, that is grams, and the same formula. That's aluminum oxide, which is the Al2O3. Now, I couldn't compare the 0.872 grams of aluminum with the 0.854 grams of oxygen. They have the same units, but not the same formula, so I couldn't compare the numbers. But if you look at these two products, the 1.65 and the 1.81, you have the same units, grams, and the same formula, aluminum oxide. Now I can compare those. So what is the smaller number of the two? Bam! It is right there, the 1.65 grams of aluminum. Now everything, for the most part, can be answered from this part right here. So the smaller number, that is the 1.65 grams of aluminum oxide, is the maximum amount that can be produced. And then from that, I can figure out what is the limiting reagent. What made that 1.65 grams of aluminum oxide? It was aluminum metal. So the aluminum metal is the one that limits it. Because you should see that the oxygen can actually produce more if there was enough aluminum. So therefore, the aluminum is the limiting reagent. Now, the other reactant is the one in excess. So here is what my aluminum is the limiting reagent because it produced the smaller amount of product and the oxygen could have produced more. The limiting reagent and the one in excess are always from the reactant side. Now we need to answer the rest of the question here. And we're going to use this setup. And we're going to figure out how much of the reactant in excess remains. So the excess reactant is oxygen. So how much do I have available to me of oxygen? This is how much I have, which is the 0.854 grams of oxygen. That's how much oxygen I have. Now I need to figure out how much oxygen I consumed and used in this problem. Now what you're going to do, you're going to take the limiting reagent, which is the aluminum, and the number and units associated with it. So the 0.872 grams of aluminum. So start off with 0.872 grams of aluminum and convert that using a monorail with stoichiometry to grams of oxygen. Okay, so I want you to pause the video, take 0.872 grams of aluminum and convert that to grams of oxygen. Pause the video and do that right now. Now this is what you're going to get. So you got the aluminum going to moles of aluminum, then using a mole ratio, and now I got grams of oxygen. This is my number in my calculator. This is my number rounded correctly. So 0.776 grams of oxygen is required. So make sure that you understand this. If I have 0.77 grams of oxygen and 0.872 grams of aluminum, I will produce 1.65 grams of aluminum oxide, and I will not have any aluminum and no oxygen left over. They will both be consumed. Okay? But how much do I have available of the oxygen? 0.854 grams. That's more than what's required, which is the 0.776 grams. So I'm going to take the difference between these two numbers right here. That is the amount that's available and the amount that's required. And this will tell me how much remains that's in excess. This is like the 14 slices of bread earlier that remained in excess. So I have 0.078 grams of oxygen remaining that's unreacted. Alrighty. That was a very complicated problem, and you're going to have to do that one again. All right, I got a nice giraffe on my head, and I hope that that problem worked well for you. You need to do that problem again, and then we are going to do the best problem of them all. So can't wait for that one, and I will see you in just a moment.